I'm Taylor Topper. I'll be your hostess for today. Just want to go over a few things before we get on with the seminar. For everyone's best interest, we do have everybody muted except for the presenters. Uh, the question pane here on the side of your dashboard, you should see something like this, typically in the right-hand corner of your screen. You can submit questions throughout the entire seminar today. Type your questions in. Some you can send to all or send privately just to me if you have a question about this seminar specifically. We'll answer these questions during our live Q&A at the end of the seminar. Without further ado, I'm glad to say that Adam Curtis is here to present for us today. Adam has been with Signacast for 17 years. He is currently the estimating manager, where he and his team develop proposals for new projects, including piece and tooling price and lead times, as well as engineering design and feedback. Adam graduated with an industrial engineering degree from the Milwaukee School of Engineering. Adam, thanks so much for presenting our first Signacast webinar.
Thanks, Taylor. Thank everybody for attending. We're looking forward to this. We do have a quick agenda here. The goal for today is to get you acquainted with the process of the investment castings, just so you can have a feel for all the steps and some of the tooling that's required and some of the things we think about as we're processing these parts. So we got a few things here, some alloy options, how the lead times will end up working when we're done, and then a few things we do throughout the process. So the first step for us is to actually build a wax tool. Now we have some flexibility in tool design. We can do manual tools, semi-automatic tools, automatic tools. So depending on part shape, part volume, complexity, we can design different types of tools to handle that. Now the tool itself is made out of 7075 aluminum in a T6 heat-treated condition. The tool is made from the aircraft grade aluminum because the cavity really doesn't wear out over time. So the wax itself is low pressure, low temperature, no abrasion, so the cavity will last essentially for the life of the project. So I'll point out a few things on the cavity and on the tool here so you can see what I'm talking about. So the cavity itself is in here, and this is just the aluminum that's been cut to form the feature. Now there are a few other things on the tool that you can see to make some other features. So there are slides and things like that. Now those do wear out over time. So we'll add some features to those to give it a robustness. So there'll be hardened Gibson rails in here on the slide, dissimilar metals on the wear plates, things like that that will reduce flash and extend the life of the tool. We also add some features like robust leader pins and bushings. Those reduce parting line mismatch over time, giving us a little better quality pattern. We do implement a cleaning and repair schedule throughout the life of the project. So as some of these wear items do actually wear, we'll put in a process to make sure we've got a good tool. Now there are some features that we add to our tool to improve the process control. You see off to the side here, there's some connections for water lines and a thermocouple. Now these are added to give us some control over the temperature of the die. So we want to maintain the die temperature from the first shot to the last shot throughout the lot for this part. So it'll give us some consistency there. And the less variation we have in temperature of our wax tool, the less variation we'll see in the size of our wax pattern. It'll give us a little more control of our metal parts in the end. Now we typically do not have to add draft to the design of the tool or the part. So as this wax pattern is sitting in here, the wax will shrink just a little bit as it's cooling, and that will allow this ejector plate here to push the pattern out of the tool with typically no draft. So it's pretty good on the design side when you don't have to fuss over adding draft to your parts. There are some things we do on the tool design to give us some flexibility in part scheduling. I'll show you some of the things we do in our plant where we like to do smaller lot sizes more often, more of a true just-in-time manufacturing philosophy. And the way we can do that are these clamp plates, PLC bundles, airline bundles. All those features allow us to quickly tear down and set up the next job on the wax press. So with short changeover times, we can do smaller lot sizes more often. Now the tools themselves, the cavities, we make most of our tools in our tool shop. And the way we do that is we take the customer's native file, Pro-E, SolidWorks, Unigraphics, or a step file, and we'll apply a shrink factor to that model. We'll then use that model to develop the cutter paths after the tool is designed in our CAD system. We'll then send the cutter paths to our 5-axis CNC machines, where we're able to cut the entire cavity, cut the mold base, cut all the water lines in place, so we can put in a block of aluminum and we can pull out a finished die half. So we have an efficient way to cut tools and to build these tools into the process. So now we'll go into injecting the wax pattern. So after the tool is built, it's designed to inject this wax pattern, and we're going to use this wax pattern to make our metal part. So we need to inject a wax pattern for every metal part that we're going to ship. And I'll show you some of the features on our wax pattern. So the pattern itself is an exact replica of the metal part that we want to make. So all the features and details you want to see in your metal piece, we're going to put into our tool and then are going to show up on our wax pattern. So for this first step, we use what we call virgin wax. So this is formulated specifically to make these patterns, and we'll use this wax one time. That virgin wax gives us a little more dimensional control throughout the process of injection and making the parts. Here at Signacast, we actually formulate our own wax. We have a facility that can make it, pump it down to the different foundries. We use it, we recycle it, and it never really leaves our plant. So we have an efficient way of producing wax within our internal plant here at Signacast. Now I'm going to have Taylor play a video for us where we can see the injection process. We're going to do the semi-automatic process first. Okay, so what you see here is the wax press opening up, and then the robot will reach inside and grab that pattern. And one opportunity we have here is the flexibility of using the robot. We can also use an operator to reach in there and grab the pattern. After the pattern is picked out of the tool, it'll be placed into the water bath to give it a soft position to land. And then the robot will finish the cycle by spraying a little mold release into the die, which is what you're seeing now. Now up above the press is a wax temperature heat exchanger where we're controlling the wax temperature to make sure each shot has the same wax temperature going in. So this is a shot of the automatic wax press where you'll see the die open up, the ejection of the patterns will just come out, and there's a water bath down below that the parts land into. The parts are then conveyed up to the operator where they'll be assembled onto the mold. So a couple other features to note on the wax pattern that you're looking at. This little section here on the back side, this is our gate. Our engineers will design a gate that will fill and feed the casting correctly. And then on the contact here where the gate meets the part, we put a little notch. And we use that notch to remove the part later in the process. And I'll show you how we do that as we get to part removal. Now that we've injected our wax patterns, we're going to assemble as many wax patterns onto a sprue as we can. So the square piece of wax that you see in the lower right-hand portion of the picture, that's our sprue. The white portion at the top here, this forms our cup. So when we attach our cup, our sprue, and the pattern itself, this becomes our mold. This mold becomes the one-piece flow throughout our plant. So we can track everything by part number, lot number, and mold number. Now what you see here is the operator welding the gate onto the sprue. And the little welding torch she has there is called a water welder. So we're just using hydrogen and oxygen. We're just burning it to make water, but it's hot enough to melt some of that wax. So we can make a little puddle of wax so the gate attaches and adheres to the sprue. So this is quite a talent to be able to create a good seal here of where this gate attaches, so we have a good contact that the shell builds correctly around this mold. So now our sprue is made from recycled wax, where the pattern itself is made from virgin wax. So the dimensions and size we're not as fussy about on the sprue. We really want to control dimensions and size on the pattern, because that's ultimately the part that we're producing. What you're looking at is they're assembling 3 to 6 of these molds onto a cluster. And there's just a large bracket up on top where we can assemble these. And this becomes our minimum lot size to run this job through the facility. We'll play a video here of showing the cluster getting assembled. Now, 3 to 6 of these assembled molds will be assembled to this cluster hanger. Once these molds are assembled, this becomes the minimum lot size to run this job through the facility. What you see now is the robot picking up that cluster that'll deliver it to the next work cell. So all the material handling is handled with an automated either conveyors or robots to move from cell to cell throughout the plant. For the shell building process, we're going to run another video here. So what you see here is that cluster then being dipped or covered with ceramic shell. And this is actually where the term investment casting comes from, is we're investing this mold into the ceramic slurry. Now there's a custom robotic program that's going to coat this entire mold with this ceramic. We're going to then back this ceramic slurry up with sand. And that's going to happen behind the robot. There's a rainfall sander constantly showering sand down that's going to coat this mold. This first layer of sand that we're going to apply is a real fine powdery sand that'll give us the surface finish and part detail we're looking for out of the casting. After that sand is applied, we're going to then open up the doors behind the robot where we're going to dry that mold. It'll take us about an hour to dry that mold, and then we'll repeat this process of ceramic and sand till we get 6 to 8 coats, about 1/4 inch to 3/8 inch thick. As we add layers of sand, the sand will become more coarse. That'll give the mold some permeability that we'll use later in the process. Now that window that the robot's placing those molds into, that's where we have the ability to dry those molds in about an hour. Typically it takes 24 hours for that drying process to take place. So Signicast has taken the shell building process from a week long down to about 1 day. All right. So now to remove the wax from our mold, we're going to use a pressure steam autoclave. So before we go into the burnout oven that you're looking at, we're going to put the mold into a vessel where we're going to pressurize that vessel before we introduce the steam. the pressurization will prevent the wax from expanding and cracking our shell. And then we'll use the steam to melt the wax out. So it'll be set on a grate, kind of like upside down the way you're looking at it right now. And most of that wax will just pour out of the cup. That wax that's poured out of the cup then becomes our sprue. So that's how we recycle our wax right away. We'll dewater it, we'll filter it, and then we'll use it for our sprues. What we don't use for our sprues, we'll send back up to our wax plant, we'll reformulate it back into virgin wax, and then pump it back down to the facility to be used again. Now that our mold is evacuated of most of our wax, now with that permeability in our mold, some of the wax is going to leach into the shell itself. So we're going to put each mold into this burnout oven. So this oven is a long tunnel, or it could be a batch oven where you just place the molds in the oven and run it through its cycle. So this oven is at 1800 degrees and usually for about 4 hours. And we're going to burn up any of that residual wax that's stuck in the shell. We're then going to cure our ceramic. We want a phase change to happen through our ceramic to make it stronger. And we're also going to preheat the mold. That preheated mold, we're going to pour our metal into while it's still hot. So we'll move on. So this tunnel that you're looking at, or this oven that you're looking at, is a long tunnel. So the molds will go in this end, and then they'll come out on the other side out to the melt deck here. So on the melt deck, we'll have an operator over here on the right, and what he's doing is he's prepping this furnace, where he'll prep about 700 pounds of metal for this heat. And he has a couple different ways of producing the alloy. We can start with like 1010 and add the elements we need to make a carbon steel, 4140, 8620. You can start with like a 304, stainless steel to make 316, things like that. We can also buy ingot of the exact alloy that we want to pour. So that's used a little more on the higher alloys and for some cosmetic parts. But for the most part, what we'll do is buy 1010 material, add the elements we need, and then produce and pour that alloy that we make. So now that the molds are preheated, the robot will reach into this long burnout oven and grab the preheated mold. We're going to use the preheated mold to allow us to do some thinner walls, and it also will prevent a thermal shock from cracking our mold as we're pouring the 3000 degree metal in. Now up on the melt deck, the operator is preparing a heat. He's got about a 700 pound furnace for each heat, and he's going to use that heat to fill the ladle. He'll finish up deslagging the ladle before the robot comes over and pours it into the mold. Down at the base of our sandbox, you can see a fire has started. That's intentional. We put some sawdust down there. So after the mold is poured, this can cover will go over the top of our mold, burning up any oxygen underneath that can. That'll give an oxygen depleted environment, allowing the metal to cool and prevent decarburization on the outside layer of our metal. So we'll get some better metal by letting it cool underneath that can. Up on each of the melt decks, there's a spectrometer. So we're checking every heat before we pour it for alloy chemistry to make sure we're within spec. So that our shell is designed to be strong at 1800 degrees. So what happens when the mold comes down to room temperature, our shell then becomes very brittle. So we use water to blast most of that shell off the mold. And that's what you're looking at here, is that shell has been cleaned off the mold, and now we're ready to remove the parts. So one of the ways to remove the parts is what you see here with a large abrasive wheel, where we can just target the gate and just cut the parts off the mold. Another method we have when we looked at our wax patterns, we have that little notch on our gate contact. And what we can do is submerge the mold in liquid nitrogen and then use that notch as a little stressorizer. And then we can just simply remove the parts by just tapping it with a little mallet or using a vibratory hammer to just quickly remove the parts from the mold. So we have an efficient way to remove most of our parts from mold. The trick with this is you need the right alloy. So carbon steel alloys, 400 series stainless steels, that allow us to use this cold break method. 300 series stainless and some aluminums and things like that become a little more difficult to be able to remove by using the break-off method. Parts are removed from the mold will then go to a finishing cell where the parts will get blasted, inspected, and gate ground. So this you can see here, the parts just set into a fixture. The fixture is then presented to a large grinding wheel. It's a big time saver belt sander where that part made contact with the gate. We're then grinding that gate contact off. So we'll have another picture of the finishing area. So the part's getting set up in the sandblaster. That's what the gal on the right is doing. It's a spinner hanger. So the parts will get blasted. Any of the shell will be blasted off there. And then the picture on the left, the robot's setting up for grinding that gate off. We could also load the fixture manually, where you'd have a tote of parts next to the gate grinder, and the operator would be setting the parts in the mold, or we can do it the way you're looking at with the robot setting the parts in the mold. Now we also have, for parts that don't blast clean, so we've used a water blast and sand blast to remove as much shell as we can from the parts. For tight areas and internal geometries where we can't blast, one of the methods we have of cleaning the parts, we call it caustic cleaning. And here, we'll actually melt salt. We use a sodium hydroxide and a sodium carbonate mixture of molten salt, and that salt will leach the excess ceramic off the outside or the inside of the part to remove that shell, and then it gives us just the metal part. We can then sandblast the part to remove any of the excess shell and any of the I guess from the salt it'll kind of look not as clean, so we'll blast that off. And typically our blast will leave about 125 RMA surface finish. We'll use a sand blaster, grit blaster to do that. We can also do some things with stainless steel shot blasting, glass bead, whatever the customer might require to finish the part. It takes about 4.5 days to get through the facility. Now that's pretty fast for the industry. We also have some parts that take weeks to get through. We had talked about before the drying time, things like that. So there are parts and operations that do take longer, but typically we can do what you saw in about 4.5 days. So after the parts get through the inspection, we'll 100% visually inspect every part, and then we'll be very product specific or part specific for secondary operations. So we have machining capabilities. You're looking at the paint line where we can finish the parts with a powder coat. The picture on the left is a heat treat oven, so we can send the parts right over to be heat treated with like normalizing, quench and temper, nitrocarburizing, things like that. So we have all those types of operations that we can do as the customer requires. So here's just a couple examples of some finished parts where we've done the powder coating. The one piece on the right gets a little pin assembled to it after we powder coat it. So we'll orbit form that pin on afterwards. This piece on the left will broach the spline, tap the hole, and then chrome plate the part. as a finishing operation, or this piece in the middle where we grind the surface flat, and then the as cast kind of forms, some dimension there to give it a good look. Now we have just some quick notes on some alloy options, because this is kind of an introduction to investment castings. We're also going to host another seminar where we're going to get into the design of investment castings. So here's just a quick overview of some alloys that we pour. This information's on our website as well, signacast.com. So next time we meet, we'll be going over the design of investment castings, how to gate, how deep of a hole can we cast. We'll explore some of these alloy options as far as carbon steels, stainless steels, your nickel-based, cobalt-based alloys. So we have a wide variety of alloys that we can pour in the commercial markets that we serve. Now the process itself is very flexible in the alloys that it can pour. So aerospace foundries will pour titaniums and aluminums. Jewelry makers use this process for precious metals, gold and silver. These are just the alloys that we focus on with the commercial markets that we serve. As we went through the process, just some of the advantages of the Signacast Hartford manufacturing complex, where we can speed up the process by controlling our in-house tooling, getting parts into production. You can see the new product launch lead time. And then as we go through the process, all of the steps are continuous flow. So as we do those smaller lot sizes more often, it doesn't take a long time to de-wax just a handful of molds. Or if you're trying to do a large batch, you could be spending a long time at one operation just to get that large lot through the facility, where the smaller lot sizes can go through much quicker. So those are just some quick notes on kind of the lead time of making parts. So 1 to 4 week lead time, with your secondary operations just adding days, because we do manage and have that equipment in our facility to be able to run. So I think at this time, hopefully Taylor's gotten a handful of questions, and everybody's got a good overview of the investment casting process.
Yeah, we have just a few questions. So just a reminder, if you have any questions for Adam, we have time now for a live Q&A. On your dashboard here, there's a questions pane. Enter your question in there, and then we'll answer it. Adam, the first question I have, how do you vent the mold?
So one thing we can do, that permeability that we've added to our mold design, that coarse sand that we add as backup layers, that will actually allow the air to escape as we're pouring metal in. So we don't have to add a vent, I guess the way you'd think of it, like in a sand casting, where you'd have your gate on one side and a vent on the other to allow that air to escape. We can actually just build our mold with one gate contact, so there isn't a secondary vent that we need to remove later. That's a great question.
Great. And we have another one. What method of blasting is the most effective at removing the remaining shell?
For us, we use the water blast. I know there's some foundries that use like a sand blast or some other material to remove that shell. And what we do with the water blast is we actually control it in some cases with a robot. So we'll program the nozzle to be able to get into different corners and blast most of that ceramic off the outside of the part. And in some cases, we can eliminate secondary operations to remove that shell. We can do it all in that first water blast operation.
Great. And the next one is, what's the benefit of the investment casting process, or benefits, I suppose, of the investment casting process compared to machining a part?
One thing that our process can do is complex geometries, regardless of the, I guess, adding complexity to the part doesn't change the price of the part. So once we assemble our mold, the pieces per mold kind of drives the cost rather than the complexity of the part. So in some cases, a highly complex machine component can be quite costly to, run that spindle or to turn that part and machine all of those features in. In fact, the investment casting industry became commercially viable during World War II because we had to machine so many parts to support the war effort. We didn't have enough spindle time, so they actually casted using this process to reduce the amount of machining that needed to be done. So going net shape or near net shape with the investment casting process became a viable alternative to some machining or some of that rough machining. So yeah, that's a great question.
That's really cool. I actually didn't know that little bit of history. The next question here is from John. What is the range of part size you can produce?
So the process itself is very flexible. We can do small parts, literally just a few ounces per part, and you can have thousands of pieces on a mold at one time, to parts that weigh, the plus side of 200 pounds. So you saw that mold, which is, 18 inches long, and it kind of has to fit on the furnace grate, which is about 12 by 14. So if you're inside of that window of part size, essentially this process can make a part, within that window of part size. Once you start getting larger than that, the wax doesn't particularly hold together well. There's some limitations once the part gets bigger than that, but yeah, upwards of 200 pounds is possible with an investment casting.
So adding to that, our next question is the opposite side, I guess. Does SignaCast do smaller, fine detail parts? So while we can do the large ones, how small are we comfortable going?
We have parts that would be half the size of your pinky nail. So yeah, we can make small parts with a few fine details on that part, as well as large parts that seemingly don't have a lot of detail, but are of a, our larger parts typically are high nickel or cobalt alloys, where machining is, excess material becomes very expensive. So we have parts like that, as well as all the parts in between, where adding complexity and adding details, once you put those features into the wax tool, it doesn't cost extra to have a hole or to have a bracket, made at this with the rest of the part. So a lot of advantages there.
Great. Next question is, how do we minimize porosity?
So that is a great question for our next presentation. We'll get into that, where our engineers designed gates in the sprue to actually feed the casting correctly. We want to control directional solidification. So we'll work with the customer on their part design to make sure that the casting is sound, and then we'll control the gate that's feeding the part and make sure our sprue is big enough to hold our gate, and then do some things with temperature. We control the temperature that the ladle is pouring the metal into. Things like that all contribute to controlling porosity inside the casting.
What is the tool capacity? What is the volume? So kind of a dual question.
So our tool capacity, like I said before, the tool will last through the life of the project. Now our tool size isn't quite based on volume of the part. So even if you have a high volume project, we'll size our tool to make enough patterns for the operator to assemble to the mold. So if we make more patterns than they can assemble, it really isn't that efficient. So most of our parts are, 4 cavities, 6 cavities, or less, just because we don't need that many cavities for the operator to make enough patterns to assemble to the mold. So we don't need a lot of cavities typically, but we will size the tool, to make to match the pieces per mold rather than, the overall volume of the project.
Great. The next question is, what process can you offer for low volume, quick turn prototype parts?
That's another great question, and we may set up our own webinar just for prototypes too. So we have a couple different options. We can make the patterns without a tool using a 3D printed wax. We have a printer here in our facility, so we can just build up layers of wax to form the geometry that we want, and we can run that wax through our process just like our injected patterns. So that gives us some flexibility for prototypes where you can build the pattern without a tool, run that pattern through the process, and it gives you production metal that you can heat treat, and you can use that for testing. You can use it for form, fit, or function, whatever you need that prototype for. So that's a great question.
Here's another one. Is one material more difficult than another to pour or control dimensions, or do all materials behave the same?
That's a great question. So some materials, let's see, how do we want to answer that? So some materials pour better than others, just with like slag and gas and those sorts of foundry defects. Most materials stay consistent within their process variation. Now, if you poured the same part out of stainless, you used the same injection mold, you used it for stainless and then poured it out of carbon steel, your shrink factors may differ, but the process variation will kind of will fall within this, the same guidance, for lack of a better way to describe it.
Great. There's a few here for inspections. What inspection methods or what standards do we use to qualify parts?
So typically for part qualification, we'll run a sample. We'll then measure, like 3 parts for each cavity, 100% to the customer's print on probably like a CMM, like a CNC CMM, where we'd run that layout and we'd be able to check every dimension on the customer's print, and we would submit that with the initial samples. We would also send those same parts out for X-ray to check for that shrink porosity we had talked about before, and verify that the gate design and part design is as we expected, and we are making sound castings, within the customer's specification.
We have a 2-part question here. Can aluminum be investment cast? And then also, what is the best surface finish that can be achieved?
Yeah, so aluminum can be investment cast. We pour typically A356, which is a common alloy for an open air casting process. There are some other alloys that can, aluminum alloys that can be investment cast. And typically the best surface finish is about a 125 RA, about 3.2 metric. And that's what you pretty much get out of the sandblaster that you finish the parts with. There are some operations we can do to improve that surface finish. vibratory tumble, things like that to try and knock down some of those high spots. You know, on the surface, you can get it down to about a 63 doing some of those types of secondary operations.
We're back to prototypes here. What do you do differently when you cast prototype parts compared to when you cast production runs?
Not much. It's more of just how many parts we make. Typically, a prototype will not fill up a cluster. If we're only making 5 parts, you know, that cluster would have 200 pieces on it. So it's essentially the same process. One thing we might do is dip the mold by hand instead of having the robot, you know, submerge the mold in slurry and cover it with sand. We might have an operator do that because the mold would be smaller. We're not running as many pieces at one time. So the process itself doesn't change for prototyping. It's just the process of making the pattern is about the biggest difference for prototypes.
Great, we have one here with injection. What is the advantage of using a robotic arm to remove a wax pattern from the tool versus an automatic process with only the ejector pins, sorry.
So one advantage of the robotic arm that we saw earlier is larger patterns that would be delicate can be safely removed from the tool. So typically our automatic injection, when it ejects from the cavity itself, we just use gravity to let it fall into the water bath. Larger parts with thinner walls, we could actually damage the pattern by letting it, you know, just fall like that. So we can use the robotic arm to safely remove it from the mold and then gently set it into the water bath, you know, the way an operator would. So it gives us that delicate touch and still maintain kind of a lights out automatic type operation.
Speaking of optimizing mold flow, this is what I think we were talking about before. So do you use Magma flow prediction modeling software or something similar?
Yeah, we do have a similar software. It's not Magma. I can't remember it off the top of my head, but it is their competitor. So yeah, we do have simulation software that we use, and we can try and predict shrink porosity in the part, or make sure the gate is feeding correctly, things like that. So yeah, we do have that software available to us.
If you're going to machine an investment cast component, how much material is typically needed for sufficient machining cleanup?
So the biggest factor in cleanup is just the size variation we might see on the part. So as the part gets larger, we'll see a little more variation in the size, typically you know, plus or minus 5 thousandths per inch. So as the part gets bigger, the part will vary a little bit more in size. So then to compensate for that, to make sure it cleans up, we may add more machine stock. So in some cases we add as little as 10 thousandths of an inch for machine stock, or in some cases we're adding, you know, 60 to 90 thousandths of an inch, depending on how big that part is. So typically it's not a lot of machine stock that we need to add, but it's mostly based on the part size to make sure the variation within that size gives us enough material to clean up.
Can you produce internal threads or undercuts in your wax pattern?
Yeah, we can. The tool that we kind of looked at is what we call an automatic tool. We have some ability to create undercuts using a water-soluble core. So we'll inject the core with this water-soluble wax. We can overmold the pattern wax around it and then leach the water-soluble wax out in a water bath with a little muriatic acid. So it kind of looks like the way a sand casting core would work, where you wrap that part around that core and then remove the core. We just do that before we attach the pattern to the mold. So it gives us some flexibility there. And then if it's an internal thread, if it's a very coarse thread, we might be able to produce it in the wax tool where we don't have to make a water-soluble core. We might be able to unscrew the thread or collapse the core and remove it that way. So there are some opportunities to do internal features or threads like that.
How do small investment cast components fare better than MIM components?
I'm not, I guess fare better, I'm guessing in price or strength. I'm not sure of the question. We do have the ability to create a very dense material where sometimes with MIM, depending on the formulation you use for your powder and things like that, you may not be 100% dense. And in some cases, investment cast can be less expensive than MIM, depending on the part size and again, the formulation that you're going for. So in some cases, MIM can hold some tighter tolerances or might be a little bit less expensive on small parts. And in some cases, investment castings win. I don't know how else to describe that for faring better, I guess.
Yeah, and I think I'll eventually write a blog post about that. So check back with us and maybe we'll have some more answers. Next question is, are sprues always one vertical bar?
Nope, we have a library of sprues that we can pick from. They can be horizontal bars and the parts will hang below the sprue. They can be what we call panels, where instead of one large vertical bar, we might have 3 or 5 vertical bars that the parts can be assembled to. So we have a lot of flexibility in sprue design. So based on the part geometry that we're trying to make, we'll change the sprue that best fits that part.
Great. Next question is, can voids or inclusions occur?
Yeah, so voids and inclusions can occur. It can be as simple as slag from the pouring process. It could be gas from the pouring process. Things like that can occur. We can get voids with shrink porosity. If the gate is inefficient to feed the part or the part design does not feed well, that can introduce voids in the process. So it is a casting process, so it is something you need to consider in your design.
Sure. What is the lowest annual production quantity for SignaCast?
We've made one. We make a part that we just make one a year. So yeah, we have a lot of flexibility there. If it's one piece or hundreds or millions of pieces. So the process itself is very flexible in how many pieces per year we need to make.
So this goes off of order quantities. Can a cluster assembly mold be quote unquote closed off to produce a smaller minimum order?
Typically what we would do, we start to lose efficiency in the plant if we were to say run only 2 molds on a cluster instead of 4. So we actually have another facility that can handle those smaller order quantities where we would run 2 molds at a time and we wouldn't put them on a cluster. We would have an operator, submerge those molds by hand and add that shell building process would be done by hand, 1 mold at a time. So we have flexibility within the different buildings that we have where we don't have to run 4 or 6 molds at a time. We can run 1 or 2 molds to fulfill the lot.
How drastically does the volume of the production run affect the unit cost?
So it's not too drastic. Once your order quantity fills up that cluster, and that cluster is ordered on a regular basis, if it's weekly, monthly, quarterly, your price kind of remains the same. It's when you drop below that order quantity, if there's spot orders or just one or two molds at a time, or the one piece order, that's when your piece price will start to change based on your annual quantity. But yeah, once you're ordering that cluster on a regular basis, your piece price kind of remains the same, regardless how many pieces you're ordering.
This one will probably be a good question to go over again more in depth during our design webinar, but what is the minimum outside radius you can consistently hold on an outside edge?
Minimum radius. So we're looking for the sharpest corner. So yeah, naturally, even if you tooled a dead sharp corner in the wax tool, when that metal cools, it's going to form its own radius. So 5 is very, very sharp for a casting. So typically about 10 thousandths, so somewhere in between 5 and 10 thousandths of an inch radius is about the sharpest we can make a part or feature.
We have time for one more question. What advantages do investment castings have over die castings?
The biggest advantage we see is the material. So investment castings can do steel, stainless steel, high nickel, things like that that are typically normal for an open air pouring type process. Or die castings, you need to limit yourself to lower temperature alloys that you can pour into a steel die. So the ceramic mold gives us a lot of flexibility in the alloy selection, where die castings, you're typically limited to alloys that the melting range is a lot lower, so you can't pour it into a steel die.
Great. We don't have time for any more questions. If you did submit a question, I will try to follow up with you after the webinar. I did jot down everybody's questions here. One of the questions though was, when is the next webinar? And we are planning to have our next design webinar in August. So be on the lookout for an email. If you received an email from me inviting you to the webinar, you should then also receive the email to the August webinar invitation. I will be sending the slides and this video recording in the next day or so, so be on the lookout for that. And as always, feedback is always welcome. Let us know what you liked or didn't like, or how we could improve for next time. Adam, thank you so much for presenting today. I really appreciate it, and I know that everyone else hopefully is walking away with a better understanding of investment casting.
Great, thanks everybody.
Have a good rest of your day, everyone.